Hi, my name is Jerry, and welcome to the third episode of Discover LlamaIndex, where today we'll be covering a very interesting and important topic on joint text-to-SQL and semantic search. And so this is actually a recently released feature within LlamaIndex, and what it covers is it showcases how you can combine the power of SQL over your structured data with semantic search over your unstructured data. And you can combine that in one package that you can use when building your LLM application. So let's get started. First is the text-to-SQL side of things. So if you think about text-to-SQL, LlamaIndex has support for text-to-SQL, and this is a pretty popular stack for structured data. The user would ask some sort of question in natural language. It would go through like a text-to-SQL prompt, essentially, from the language model. And you can get more complicated than this. You could build an entire system around text-to-SQL, be able to infer the table schemas, store the table schemas themselves inside of a vector store. But fundamentally, imagine some sort of prompt that you're sending to the language model that says, here's a set of schemas for my data collection. Here's some example rows. And then given this, can you generate a SQL statement given the query that's coming in? And it turns out models like GPT-3, GPT-4 are pretty good at doing text-to-SQL. And you can actually basically just like compile a natural language into SQL as a declarative language and execute the SQL statement against a SQL database and get back a final answer. The thing about SQL, which is kind of nice, is that it's an extremely expressive language for tabular data. If your data is organized in some sort of structured format, it can perform aggregations, joins, windowing, a lot of these different things. And some example queries that would work for this types of for like a text-to-SQL use case really are about like queries for structured analytics. It's like the types of questions you want to ask to get some sort of like statistics or insights from your tabular data. For instance, some questions that you might ask are, what is the average population of cities in North America? And what are the largest cities and populations in each respective continent? Now let's talk a little bit about semantic search over unstructured data. For all of those of you who are starting to build LLM applications, inevitably you've kind of come across this basic stack, which is you store your unstructured text in some sort of vector database. So you ingest it from a data source like a PDF or API, you chunk it up, throw it into a vector database, whether it's like in memory or Pinecone or Chroma or Weaviate or etc. And then once you actually have the data in a vector store, you set up some sort of retrieval augmented generation system that combines a retrieval model with a synthesis model. So when an incoming natural language question comes in, what essentially happens is that you would first perform a retrieval step of embedding the question and then using that embedding to look up the top K most similar documents from your vector database, retrieving those similar documents, and then given those retrieved documents, feed it into some sort of synthesis model, which uses the language model to generate a response given the context that's injected into the prompt. And so this is the basic stack that's emerging for kind of like asking questions over your unstructured data. And if we just like kind of take a step back and think a little bit about kind of the benefits of like asking questions over unstructured data, there's certain types of questions that require making sense of just like unstructured text. And maybe it's not super obvious about how to convert this text into a tabular format to begin with. And so for instance, like if you want to ask a question describing like a certain scene or a certain event in history, or asking about a certain event, those are questions that are well suited for semantic search. Some example queries here is, tell me about the historical museums in Berlin. Like, don't just give me the number of them, like actually describe in plain English, like, exactly what museums are there as well as the history behind them. And then another question is, from The Great Gatsby, what does Jordan ask from Nick on behalf of Gatsby? And you actually have to go in and retrieve the actual dialogue from this conversation in order to get back an accurate answer. So I think one question that we've been asking ourselves that motivated the release of this feature is, what if you could combine the two? Somehow combine the power of an expressivity of SQL over your structured data with the unstructured context that you can get from storing unstructured text in a vector database. So that's how we propose this new feature called joint text-to-SQL and semantic search. For instance, let's say, let's just take an example use case for this. And this example use case is, tell me about the arts and culture of the city with the highest population. And this is the question that you want to ask over your data. And ideally, you want to build an LLM application that can satisfy this query. Let's walk through some of the expected steps maybe that a human might do when they actually want to fulfill a query like this. So first, you want to query for, okay, what exactly is the city with the highest population? This is very suited for instance, like a structured analytics query like text-to-SQL, because it really is just about getting kind of like a statistic from a table, assuming you have that table data of cities and populations. And so you could just do something like select star from table where and just do like order by population, right? And then let's say the response here is Tokyo. After you get back the city with the highest population, you probably want to refine the original question because now you have more information. So you want to say, tell me about the arts and culture of Tokyo. And this is a question that you actually want to ask over the vector database and do semantic search. And so you ask this question. And the interesting thing is for a lot of these vector stores, they offer a more interesting interface than just kind of like a natural language query nowadays or an embedding lookup. You can actually specify, for instance, like metadata filters, like basically structured tags in addition to the unstructured data so that you can effectively like filter for relevant content. And so you can ask this question over a vector database and supply the relevant metadata tags and get back a response. Some popular events and festivals in Tokyo include, et cetera, et cetera. You could, look this up from the Wikipedia article. And then you want to combine all the intermediate steps into a final answer that you would surface to the user. So if you think about like steps 2 and 3, it's roughly similar to, for instance, like joining, like two tables together within a structured database. But here you're effectively joining information from your structured data, which is, what's the city with the highest population, with the unstructured context within your vector database, which is, okay, now that we know it's Tokyo, can we fetch information, from this unstructured corpus to tell me a little bit more about the arts and culture scene? Here is a rough diagram of how this entire, flow could that be packaged into a feature, and this feature actually is, the feature that we released in LlamaIndex. And it's a pretty robust query interface that can effectively join both your SQL database as well as your vector database, as well as query each one independently if it needs to. And so I'll talk a little bit about what this means. But as the basic example, given the example that we just showed in the slides, let's say the query is, tell me about the arts and culture of the city with the highest population. You would first hit some sort of selector. So given the question, you first want to decide, okay, well, like, is the query, like the first step for this question, should we, hit a SQL database, or should we just directly go just do semantic search over a vector database? For this question, because we need to know what the city with the highest population is, we're going to route this query to the SQL database. The SQL query engine that we have in LlamaIndex can then run text-to-SQL over this query to then translate this query into the structured analytics query. What is the city with the highest population? That can then run as a SQL statement against the database. You get back the response, Tokyo is the city with the highest population. Then you would come up with some sort of query transformation module step that takes in this information so far from the SQL database, the original question, and then you return a more detailed question. What are some popular festivals and events in Tokyo that celebrate its culture and art? Notice that from this query transformation step, you could actually just come up with the final answer if you wanted to. And for instance, if the query really was just something that you could just directly get from some sort of like text-to-SQL query without needing to augment with any sort of unstructured context, then you could actually just return a final answer without needing to go through the vector database. So if the original question is, what is the city with the highest population? Then by the time you get to this step, you actually don't need to get to the vector database. You already got all the results from performing text-to-SQL over the SQL database. But back to the original question, you ask what are some popular festivals and events in Tokyo that celebrate its culture and art, you would hit the vector database query engine. And then, this will actually hit the auto retriever module, which was also a recently released feature in LlamaIndex that can take in this query and actually infer the right, not only just like the query string, but also the metadata filters that you need to supply to hit the vector database. And finally, once you actually get back a response from the vector database, you would join that response plus all the intermediate steps to get back a final answer. So without further ado, let's walk through an example notebook just to showcase how this works. So in this example, I'm just going to zoom in really quick. We'll show you how to use we call this the SQL auto vector query engine, and we'll show you how you can actually set this up step by step. So first, we'll just do some basic imports. I'll restart the kernel really quick. Great. Okay, so notice that we just import some basic constructs so that we can set this up. The other thing we're going to set up is our pinecone index. So if you have followed our tutorials, this is just the basics of how you can use the pinecone library, get your API key, create an index, and then just for the sake of completeness, we'll make sure to clear it. This part is just configuration. We set the chunk size to 1024. We define an LLM predictor, service context, all these things. And then we also define a pinecone vector store. So like pinecone is going to be used for our vector database. For our SQL database, we're actually going to be using SQL Alchemy. And so we're just using a SQL Alchemy is basically a Python library that hooks up with any sort of structured database, and we're just using SQLite here. So here we're creating the SQLite database, and here we're just going to create a sample table. And so going along with the example from the slides, we're just going to create a table called city stats that contains city name, population, and country. And so this is the structured table that contains all these population statistics. Oh, okay. Let me just recreate this real quick. And here we're just going to insert some 3 data points, Toronto, Tokyo, and Berlin. And the populations are around, like 3 million, 14 million, 3.6 million. My numbers might be totally off, by the way, but this is just for an example. Okay. Great. And so we're also just going to load in the Wikipedia articles corresponding to each city. We can do this with the Wikipedia Python package, and we also have a Wikipedia reader within LlamaIndex that can load in the unstructured articles for each city. Great. Now, given that we have the data and the basic setup done, we're just going to build the SQL index to basically interface with this SQL table that we just set up, and then we're also going to build the vector index over the Wikipedia articles. Notice that here we actually set up one vector index, and this vector index contains articles from each city, but each city has metadata tags associated with it. So these metadata tags include the title, and we insert the city corresponding to each chunk. Next up, we're going to define the query engines for both the SQL, the text-to-SQL engine, as well as the vector store engine. So here, we're defining the SQL query engine. And here, we're defining a custom retriever query engine over your vector store. And this specifically uses this thing called a vector index auto retriever. So there's basically 2 ways of interfacing with the vector store in LlamaIndex. One way is just pretty simple. You take the question, get an embedding from it, and just directly do some sort of embedding lookup from the underlying vector store. The auto retriever is a step up in sophistication in that given some sort of input query, you can actually infer not only just the input query, but also any sort of additional metadata filters that you might need to supply in order to filter out the right information from the vector store. So certain providers like Pinecone and Chroma have this already built as an interface. And the nice thing about the auto retriever is you can actually use the LLM to then infer the right tags to hit the vector store with. This is nice because this allows us to do better join capabilities with the SQL database when we subsequently hit the vector store after getting back some initial results from the SQL table. The next thing we're going to do is just wrap these two things as tools. And a tool, you can kind of think about it in the context of like agents and tools, but this effectively is just letting it be used by this downstream query engine. Cool. After all the setup, we have some of the good stuff here. So we're going to define the SQL auto vector query engine right here. Takes in the SQL tool, the vector index tool, and then also some additional configuration. And with that said, we're going to run 3 queries. One is a query that does make use of both the SQL database and the vector database, and is exactly the same example that I showed in the slides. And then we'll also run through some examples where you might actually only need to hit the vector database or the SQL database. So let's run through this example. All right, so query is tell me about the arts and culture of the city with the highest population. And first, we'll query the SQL database because we are able to infer that given this question, we first need to figure out what the city with the highest population is. Notice that the SQL query is select city name population from city stats, order by population. And then you get back a response. Right? Tokyo is the city with the highest population. This part is probably hallucinated by the LLM because this part is not in the SQL database. But nevertheless, you have this information, and going along with our diagram right here, we then get a new question given the SQL response. What are some more specific art galleries, museums, and festivals in Tokyo? You then query the vector database with this. Some specific art galleries and museums in Tokyo include, the Nezu Museum, the National Diet Library, National Archives. And finally, everything is combined to give you back the final response. This is something you can definitely try yourself. Another nice property of this is that you actually don't need to have, for instance, like exact matches between your vector database and your SQL database, because a lot of this is just like inferred by the LLM. And so just like, given any sort of rough relationship between your data and like a SQL database and vector database, you don't need to set up like an explicit data model. We could have the LLM infer that for you. For completeness, this is the final response. The next example I'm going to show is what if you just want to ask a question that doesn't really need the help of the SQL database, really. Like this information can just be found by doing semantic search over your documents. So tell me about the history of Berlin. Remember the selector in the beginning, it's able to actually detect whether or not this question should hit the SQL database first or just go directly to the vector store. In this example, notice that the first step is actually just going directly to the vector store. And then once we actually go to the vector store, we can just fetch the relevant context to get back the useful context for answering the question. Great. So this is the final response that you get. Finally, let's ask a question that actually only requires the SQL database and doesn't require the vector database at all. So remember in our diagram, once we hit the text-to-SQL database, we can actually have some sort of additional query transformation or processing step that decides, okay, should we then translate this into a question that we want to hit the vector database with, or are we actually good? Are we done? We don't need to do any further steps because the question's already been answered. So here we ask, can you give me the country corresponding to each city? Notice that, okay, we query the SQL database. And the SQL query is select city name, country from city stats. And we get back a response. Toronto's in Canada, Tokyo's in Japan, Berlin's in Germany. And notice how we actually don't have a follow-up query to ask the vector database with, because the question has already been answered. Great. And that's it. would definitely encourage you to try out the notebook. It's linked in the YouTube and also in the docs as well. And if you have any questions, please hop on our Discord and feel free to shoot us a note. Thank you.